Welcome learners. In today's lecture, we are going to continue our discussion and look into the second behavior of a RLC circuit, and this time we are going to look into the equations of voltages and currents for a series RLC circuit. We are going to again derive the expression for the voltages and current for the natural response of a series RLC circuit, and then we'll just look at the step response behavior of a series RLC circuit. So first we start with the natural response of a series RLC circuit. So in the natural response, we will look into the voltage and current expressions that govern the behavior of this kind of a circuit. And we are going to come to this conclusion that the equations which we derived for the parallel response or parallel RLC circuit, the equations in terms of voltages will be equal to the equations for the current that we are deriving for the series RLC circuit, and we are going to shortly look into this phenomena as well. So let us start with the natural response. This means that our circuit is going to have all the components, the circuit elements of resistor, inductor and capacitor connected in series, and since these are R, L and C, and since this is a natural behavior, so the configuration is not going to involve any voltage source or a current source for that matter. This means that the source has been abruptly removed, and thus we are left with the natural response circuitry shown here. Since this is a series network, we know that the first thing or the easiest thing to find is the flowing current, as the behavior of current remains the same, and the initial values appearing across the capacitor will be V0 for the initial voltage, and the I0 is the initial current that was available prior to the abrupt disconnection of the sources. So let us apply the Kirchhoff's voltage law, and in this case KVL, to find the same amount of current flowing through this circuit. So when we apply KVL, let us say if this is my node to begin with and we move in the clockwise direction. So the first thing we encounter is the voltage across the resistor, summing it with the voltage across the inductor, then voltage across the capacitor, and this must all come to be equal to 0. So let's input the values. So we know that voltage is equal to IR, then the voltage across the inductor is L di by dt, and then for the capacitor we have the 1 by C integration from 0 to t I d of t plus V0 equals to 0. Again, this is the capacitor model equation that we have used, where it is having the value of V0, the initial voltage, and then the rate of change of current as the time changes in the form of integral of I dt. So now let's differentiate this equation with respect to t. So let's differentiate complete equation with respect to d by dt. So our equation will have this form. So d by dt IR plus L di by dt plus 1 by C 0 to t I dt plus V0, and everything equals to 0. So now once we differentiate it, the equation will be R, then it becomes di by dt plus L d square I by dt square plus this will become 1 by C 0 to t I dt, and this will be d by dt equals to 0. This is a constant, so it will automatically be differentiation will be equal to 0. Then we'll be left with R di by dt plus L d square I by dt square. Integral and differentiation cancels out, so we'll be left with I by C equals to 0. Let us divide the complete equation by L in order to find the current. So we divide the complete equation by inductance L. So we'll have R by L di by dt plus d square I dt square plus I by LC equals to 0. Now once we have this, we can see that this is a second order equation. If I write it in form of the second order, d square I dt square plus R by L di by dt plus I divided by LC equals to 0. So this equation with the power of or the exponent being 2 is basically a second order differential equation. So how can we solve this? Again, we cannot use the separation of variables method. So we are basically going to take the same assumption which we did with the previous derivation of a parallel RLC circuit, and the assumption that we are going to take is basically we are going to assume from the first order differential equations that our unknown, which is current in this case, will depend upon an coefficient A multiplied by an exponential power s of t. Again, this is the assumption that we are taking based on our output we got from the first order natural response of RL and RC circuits. So we take the value of I and we put it in equation. Let us say if this is my equation 1, so I'll put this in equation number 1. So once we do that and do the differentiation, we will get A s square e raised to power st plus R by L A s e raised to power st plus A e raised to power st divided by LC equals to 0. Again, we can take the common factor of the coefficients A e raised to power st, which will be s square plus R by L into S plus 1 by LC equals to 0. And you can see we are again moving towards the formation of the equation, where in this expression this will be like this. So in this expression we will basically have two elements equating to 0. We can say, and we know that this element cannot be equal to 0. So A e raised to power st cannot be equal to 0, because if we take A equals to 0, this means that our initial current will be 0, and we know that inductor does hold an initial current value of I0. So this value of A or coefficient of A cannot be equated to 0. Similarly, the exponential is having a power of t, which means that it is going to vary from 0 to infinity, and it cannot be completely 0. The only time it is going to be 0 when the value of t becomes infinite. So exponential power infinite will lead to 0. This means both of these elements are not equal to 0. So the only thing that will truly be equal to 0 will be the value inside the parenthesis, which will be s square plus R by Ls plus 1 by Lc equals to 0. And again, we can see that this equation can be solved by using the quadratic equation, because we are having the exponent power of 2. So if we use the quadratic equation to get the roots, so the quadratic roots are given through this equation by using the famous quadratic equation of x is equal to minus b plus minus b square minus 4ac divided by 2a, and thus we get the two roots from the quadratic equation being s1 equals to minus r by 2l plus minus under root r divided by 2l whole square minus 1 by lc, and the second root comes out to be, so this is basically s1 and s2, and we can see that these are the two roots that can be used to define or find the unknown current for a series RLC network. And we can further write these two roots in the form of Neper and resonating frequency, where S12 can be written as minus alpha plus minus alpha square minus omega naught square. So this is the second form of writing the roots, where we know that, so I can say this is my equation number 2, and equation number 3 is basically another way of writing the roots, where now we know that the Napier frequency alpha is basically r divided by 2l with the units of radian per second, and the resonating frequency omega naught remains the same, which is 1 divided by under root LC. So these are the values that is going to help us in finding the roots of the equation, and we can now put these values of roots back into equation number 1, and from there we can see that putting the roots back into the assumed equation, back into equation number 1, gives us the final equation for current, and it comes out to be A1 e raised to power S1t plus A2 e raised to power S2t. And to our surprise, that this equation resembles the same equation we had for the overdamped response. So we can say that this is the overdamped response, but this time this is representing the current, and previously the same thing was, or the same equation was given to us in terms of the voltage V of t when we talked about the parallel RLC natural response. So as I mentioned in the beginning, that we'll come to this realization from the derivation that the equations which we got for the natural response of a parallel RLC circuit, all the voltage equations will be the same. The only thing will be that in the series RLC, the equations will be represented for the currents or the unknown currents. This means that without going into the further derivations, we can assume, or we know, that the equations for the underdamped and the critical damped equations of voltage seen in the natural parallel RLC circuit will be the same for the series RLC circuit when finding currents. This means that our underdamped equation will resemble the same structure, which will be B1 e raised to power minus alpha t cos of omega dt plus B2 e raised to power minus alpha t sine of omega dt. So this equation is for the underdamped response of the current now. And similarly for the critically damped, we will have d1t e raised to power minus alpha t plus d2 e raised to power minus alpha t, and this is for the critical damped response. So again, the equations are almost having the same exact behavior as we saw with the parallel RLC circuits, and our omega d for the underdamped remains the same as omega naught square minus alpha square. So this is the similarity that we are getting, and we can say that the series RLC behavior, since we found the current I of t, is similar to the parallel RLC behavior where we found the voltage equation. So this is a very important term, or the relationship that we should know whenever solving the series or parallel RLC networks. So this is the conclusion that we have. Similarly, if we just go to the next proof, which is the step response. So now we know about the natural response of a series RLC circuit. Similarly, we can see the step response of a series RLC circuit, and the step response is going to be similar to what we saw previously. In the step response, we know that our circuit again will have the components, circuit elements connected in series. So this is your capacitor, inductor and resistor. The only thing that makes a circuit in a step response is that we add a switch and we suddenly apply a source, in this case a voltage source, and thus at a certain time, let's say a time equals to 0, when the switch gets closed, the elements will be supplied with this voltage source of V of S. Thus the voltages appear will be V of C, V of L and V of R across the series elements. So this is how the step response behaviors work, and we know that the equations for the current and voltage will remain the same. The only thing is that we are going to add the sudden or abruptly applied voltage source. This means that our final equations, let's say V of C for the overdamped case, will be V of F, which is the voltage source applied, plus our original equation, which can be written as A1 e raised to power S1t plus A2 e raised to power S2t. To differentiate, we just add the bar sign. Similarly, the second equation for the underdamped response will be again voltage source, which we can say as the final voltage, plus the previous equation, which is going to be B1 e raised to power minus alpha t cos of omega dt plus B2 e raised to power minus alpha t sine of omega dt. Again, we add the bar sign to differentiate the coefficients. And finally, for the critical damped step response, Vc will be equal to V of F, which is the final voltage, where we are considering final voltage to be the voltage source applied, and the equation will be d1 bar e raised to power minus alpha tt plus d2 bar e raised to power minus alpha t. So again, the step response behavior behaves in the same way in terms of equations which we saw previously, and the same formulation will go for finding the currents. Just apply the final value. In this case, it is going to be I of F plus the same equations for the series RLC natural behavior. So this is basically the step response of the series RLC circuit. To conclude this lecture, let us have a look at an example and see how can we find the series RLC behavior. So let us say we have this example with us. To better understand the idea, we say we have this circuit with a capacitor, a switch, followed by an inductor and a resistor. So resistor is having a value of 560 ohm, inductor is 100 millihenry. The switch is going to be closed at time equals to 0, which means that our circuit is now in the step response, where the capacitor is having capacitance of 0.1 microfarad, so it is going to discharge the energy at time equals to 0, and the voltage applied on this capacitor is 100 volts. So this is the energy that is being given by the circuit. So 0.1 microfarad capacitor is charged through this 100 voltage source, and at time is equal to 0, the capacitor is going to discharge energy through the resistor and the inductor circuit elements. So what we can say is that initially the voltage at the capacitor is going to be 100 volts, and the initial inductor current given is 0 amps. In this case, we need to find the current when time is greater than equal to 0, and we also need to find the voltage across the capacitor when the time becomes greater than equal to 0. So these are the two unknowns that we need to find given the circuit. So let us begin the solution with the first part. So in the first thing, whenever we are dealing with the natural or step response of a parallel or series RLC, is to figure out which kind of response this circuit is giving us, whether it is an overdamped, underdamped, or a critically damped. So the first and foremost thing is we need to find its roots. So we always start by finding the roots of this circuit. So roots basically going to let us know which current or voltage expression we need to find. Since this is a series network, so we are interested in finding the current I of t, but for which response, that is going to be figured out by using or finding the roots. So finding the roots for a series RLC, we first find the value of alpha, which is R divided by 2L, and the resonating frequency is 1 divided by under root LC. The relationship between these two is going to let us know what we are having. So if you remember, if omega naught square is greater than alpha square, we say it's an underdamped response. If the resonating frequency is less than alpha square, we say it's an overdamped response. And if they become equal, we say it's a critical damped behavior or a response. So these are the conditions which are going to assist us. So let us say the Neper frequency comes out to be 2800 radian per second for this value of resistor and inductor, and the resonating frequency comes out to be 10 raised to power 8 radians per second. So we can see that here the second condition or the first condition is getting fulfilled, which means that the system is a underdamped behavior because omega naught square is greater than the Neper frequency square. Since this is the case, we know that the current can be figured out by using this equation. I of t is equal to b1 e raised to power minus alpha t cos of omega dt plus b2 e raised to power minus alpha t sine of omega dt. So this is the expression for the current which is going to help us solve this problem, and we know that here omega d is basically under root omega naught square minus alpha square, which comes out to be 9600 radians per second. So we have figured out omega d in this equation. So we know what is the value of omega d for the trigonometric identities. Now we need to figure out the coefficients b1 and b2. So in order to find the coefficients b1, we know that b1 is basically dependent upon the initial current when the base equation is having a value of t. So in this equation, if we put time equals to 0, we get the value of b1 equals to be initial current. So initial current given is 0 amps. So this means our first coefficient is 0. Now let us find the second initial condition or second coefficient b2, which is basically equated by again taking the derivative of this base equation and then putting time equals to 0. So b2 comes out to be di 0 plus by dt, and again this is the equation which is taken from the current equation of the inductor. So it is equal to v naught by L, and now we know that the initial voltage is 100 divided by initial inductance is 100 millihenry. So it comes out to be 1000 ampere per second. So this is the value of initial voltage, which is this condition. So now in order to find b2, we just use di 0 plus by dt. So initial condition or rate of change of current is equal to minus alpha b1 plus omega t b2. So this equation is basically going to give us the unknown b2. So once you input all the values, b2 comes out to be 0.104 amperes. So this is the value of the second condition. Therefore our final current, the unknown current or the expression for current I of t when time is greater than equal comes out to be 0.104 e raised to power minus 2800 t sine of 9600 t amps. Again condition is important when time is greater than equal to 0. So this is the unknown currents expression which we have figured out for the first part. And now in the second part we need to find the voltage which will appear across the capacitor when the time is 0. So initially it was 100 volts. Now what is going to be the time appearing when the switch has been closed? So we can either apply KVL, where it is the voltage across the resistor plus voltage across the inductor, which is di by dt, or we can directly find the voltage across the capacitor using the second form, which is IC 0 to t dt plus initial voltage of V naught, which is 100. So any of these two equations can be used to find the voltage across the capacitor. So finally the voltage across the capacitor when time is greater than equal to 0 is 100 cos of 9600 t plus 29.17 sine of 9600 t exponential minus 2800 t volts when time is greater than equal to 0. So this is the output voltage expression for the given series RLC circuit.